Now I would like to show you a few slides, and I might as well cover this up so that we get it very dark in this room. I want to show you the Crab Nebula, and I think I will also show you the beautiful flywheels in Magnet Lab. Now I need a flashlight. I need my laser pointer. I need a lot of stuff. Okay, there we go. So I'm going to make it dark. You ready for that? Okay, if I can get the first slide. What you see here are these flywheels at the Magnet Lab. These are the wheels that have a mass of 85 tons and that have a radius of 2.5 meters. An incredible, ingenious device, and you can store in there 200 million joules, and you can dump it into magnetic energy and in 5 seconds dump it back into kinetic energy of rotation. It's an amazing accomplishment, by the way. And here you see the Crab Nebula. The Crab Nebula is at a distance from us of about 5,000 light years. It is the remnant of a supernova explosion in the year 1054. Much more about that during my next lecture. And what you see here is not stuff that is generated at this moment in time by the pulsar. This, by the way, is the pulsar. And the red filaments that you see here is material that was thrown off when the explosion occurred. The explosion, the supernova explosion, throws the outer layers of the star with a huge speed, some 10,000 kilometers per second, into space, and that is what you're seeing. From here to here is about 7 light years, to give you an idea of the size of this object. This pulsar alone, however, generates the 6 times 31 watts. And we do know that it is this star that is the pulsar, and we know that it is not that star. And the way that that was observed, that was measured, is as follows. A stroboscopic picture, a stroboscopic exposure was made of the center portion of the Crab Nebula. And a stroboscopic picture means that you are using a shutter which opens and closes. In this case, you have to open and close it with exactly the same frequency as the rotation of the neutron star. This neutron star, for reasons that is not well understood, is blinking at us. It blinks at us at exactly the frequency of its rotation, 33 milliseconds. That means 30 hertz. Roughly 30 times per second, you see the star become bright and then go dim again. If now you set your frequency of your shutter, in front of your photographic plate, at exactly that frequency, and you expose the photographic plate only when the star is bright, then you will see a very bright star when you develop your picture. If now you take another picture, expose it the same amount of time, but the shutter is open when the star is dim, and you develop that picture, the star is dim. But the beauty is that all other stars in the vicinity, of course, will show up on both photographic plates with exactly the same strength because they are not blinking at you. Since they don't blink at us with a period of 33 milliseconds, and that is what you will see on the next slide, which is a stroboscopic exposure. This star is clearly not the pulsar, as it is about equally bright on both exposures. This is not the pulsar, but this one is. You see, this one is missing here. And so this is beyond any question that we know exactly which the pulsar is. Very new observatory was launched only recently, and that is called the Chandra X-ray Observatory. And Chandra made a picture very recently of the Crab Nebula. of the pulsar. And that's what I want to show you now. It's on the web. And I show you a picture that many of you probably haven't seen yet, which is the center part of the Crab Nebula. And the pulsar is located here. And all this is X-rays, nothing to do with optical light. This is all X-rays. And you see there is a huge nebula here around this pulsar, which is about 2 light years across. And all that energy in X-rays is all at the expense of rotational kinetic energy of the pulsar, which is quite amazing. And when this picture was made with Chandra, X-ray Observatory, they discovered immediately that the pulsar also produces a jet. Maybe you can see that from where you are sitting. There is a jet coming out here, and with a little bit of imagination, you can see this jet going out there. And all that energy is at the expense of rotational kinetic energy. MIT has a big stake, by the way, in the Chandra Observatory. And not only MIT, but Cambridge as a whole. The Center for Astrophysics and MIT are running the Chandra Science Center, from which all radio commands are given, which is here just across the streets, a few blocks away. And many MIT scientists have dedicated a major part of their careers in this endeavor. And these are one of the wonderful results that have come out. So see you Friday.